Okay, picture this. The year is 1911. A Dutch physicist, Heike Kamerlingh Onnes, is chilling mercury down to temperatures colder than deep space. He's watching its electrical resistance, and just like he expects, it's dropping. But then, something absolutely impossible happens. The resistance doesn't just get low, it vanishes. Gone. As you can see right here in his original data, it just plummets to zero. And just like that, one of the greatest mysteries in modern physics was born.
I mean, how is that even possible? How could a material suddenly decide to offer absolutely zero resistance to electricity? This question became the superconductivity puzzle, and it was a riddle that would stump the world's best scientists for nearly half a century.
So at first glance, you'd think, okay, we've got a perfect conductor, right? Problem solved. But oh no, as we're about to see, the truth is so much stranger than that.
And here's the really wild part. This change isn't gradual at all. It's like a switch gets flipped. At a very specific critical temperature, or TC, the material just instantly transforms into this bizarre new state. For mercury, that's 4.2 Kelvin. We're talking minus 452 degrees Fahrenheit. It's a genuine phase transition, just like water freezing into ice. But for electrons, it's incredible.
So for a while, everyone just ran with that idea. Perfect conductor, case closed. But they were so wrong. The story was about to get much weirder.
Fast forward 22 years. Just when the mystery was getting cold, a new experiment by two scientists, Meissner and Oxenfeld, revealed a second, even more bizarre property that proved this wasn't just good conducting. This was a completely new state of matter. So, when the material is warm, above its critical temperature, a magnetic field passes right through it. No problem. But look at the image on the right. The moment it becomes a superconductor, it actively pushes the magnetic field out. It's not just ignoring it, it's creating this invisible force field around itself. This is what's known as the Meissner effect.
And this is the real kicker. This is the smoking gun. See, according to the physics of the time, a so-called perfect conductor should actually trap any magnetic field inside it when it cools down. But a superconductor kicks it out. This was proof positive that we weren't just looking at perfect conductivity. This was something fundamentally new.
But, this incredible new state of matter is also, well, it's a little bit fragile. It only exists within very strict boundaries, which adds a whole new set of rules to our puzzle.
First off, every material has its own unique critical temperature. And for these early materials, those temperatures are unbelievably cold, just a few ticks above absolute zero. I mean, even that niobium germanium, which was a record breaker at the time, has a critical temperature of 23.2 Kelvin. That's still a mind-numbing minus 418 degrees Fahrenheit.
But temperature isn't the only thing that can break the spell. If you hit it with a magnetic field that's too strong, what we call the critical field, boom, the superconductivity just vanishes. It snaps right back to being a regular old material. The same thing happens if you try to pump too much electrical current through it. There are very clear limits to this magic.
And just when scientists thought they were finally mapping out all the rules, bam, they discovered the puzzle has another layer. Turns out we're not dealing with just one kind of superconductor. There are actually two.
So have a look at these graphs. A type 1 superconductor, that's the one on the left, is pretty straightforward. It pushes out the magnetic field completely until it hits a single critical point, and then it just gives up. But type 2, that's a whole different beast. It perfectly expels the field up to a lower point, but then it enters this weird vortex state, where it lets some of the field lines sneak through, all the way up to a much higher limit.
Okay, so let's break that down. Type 1s are usually pure elements, and they have that clean, all-or-nothing Meissner effect. Type 2s are typically alloys and compounds, and that amazing ability to handle super strong magnetic fields in that mixed state makes them way more useful for things we actually want to build, like the incredibly powerful magnets inside an MRI machine. All right, let's recap our detective file. We've got zero resistance, we've got magnetic fields being kicked out, we've got these critical limits on temperature, field, and current, and we've got two different types. But the biggest question of all was still just hanging there. How? What is actually happening down at the atomic level to make all of this possible? The climax of our story is the breakthrough that finally put all the pieces together. You have to understand, for nearly half a century, 46 years to be exact, this mystery just completely stumped the smartest people on the planet. And then, in 1957, three guys, John Bardeen, Leon Cooper, and Robert Schrieffer, they finally cracked it with what we now call BCS theory. And the core of their big idea was something that sounds completely wrong. We all learn in school that electrons are negatively charged, right? And things with the same charge push each other away. So how in the world could two electrons possibly team up?
Well, the secret wasn't just in the electrons themselves. It was in the world they were living in. See, a metal isn't empty space. It's a structured grid of positive atoms, what we call a crystal lattice. Think of it like a perfectly organized, three-dimensional jungle gym.
Okay, so now imagine one electron, E1, zipping through this jungle gym. As it flies past these positive atoms, its negative charge gives them a little tug, pulling them inward just a tiny bit. It creates this temporary ripple, a little pocket of extra positive charge right behind it. It's kind of like rolling a heavy ball across a soft mattress. It creates a momentary dip.
So now, here comes a second electron, E2, and it sees that dip, that little pocket of positive charge, and it's attracted to it. That tiny attraction, mediated by the lattice vibrations, is just enough to overcome their natural urge to push each other away, and they link up, forming what we now call a Cooper pair. And this team, this duo, can now surf through the lattice together, totally unimpeded, zero resistance.
And there it is. That was the key. This one brilliant idea of Cooper pairs suddenly made everything else make sense. Zero resistance, the weird magnetic effects, all the clues just clicked into place. After 46 long years, Bardeen, Cooper, and Schrieffer had finally unlocked the mystery. So, BCS theory was an absolute triumph. It cracked the code for how superconductivity works in the freezing cold. But it also left us with the next great quest, the holy grail of materials science. Can we do this at room temperature? Can we engineer a material that gives us this incredible power, this effortless flow of energy, right here, right now, without needing any cooling at all? That is the puzzle we're still trying to solve today.